Okay, hello guys, welcome to this tutorial. And today we are going to be looking at response surface methodology, RSM. Some of you may know RSM and others don't. So I'll quickly give an overview on response surface methodology before we head over to the analysis. So RSM is a powerful statistical and mathematical technique used for optimizing processes, improving product quality, and understanding the relationships between input variables and response variables. RSM is particularly valuable in industries where experimentation and optimization are essential, such as manufacturing, engineering, chemistry, and product design. Okay, so to explain this RSM, I will just um, divert for a while, so I will you all understand what I'm trying to explain. So let's come over here. Okay, over here we have some condiments. And definitely this is going to lead to a spaghetti. Sorry if you are watching from other countries. This is just an example. So let's just flow with this. Over here, so we have an onion, we have eggs, we have oil, we have pepper, we have spices, we have tomato paste, as you can see right here. Now, definitely, no matter how you prepare this, you are going to end up with spaghetti, right? But once you begin to alter these condiments, you are going to end up with spaghetti, but the spaghetti is going to taste differently depending on what and what combination you use for that particular spaghetti you cooked. Okay, say for instance we used one onion, as you can see here, we used two eggs and everything, as you can see here. It's going to give us a spaghetti that tastes particular that has a particular taste. Now if you begin to alter this, let's say we use two onions and whatever, we add more eggs, we use more salt, and we use more spices, definitely our spaghetti that we get as the output is going to taste more spicy or salty at the end of the day, right? Now we must still further go ahead to try other combinations, like let's say using more pepper, using more bulbs of pepper, and more oil, etc. Our output spaghetti at the end of the day might taste more pepperish than the rest. So we find out that various combinations are going to give us various outputs on the spaghetti. So what RSM is trying to do is trying to give us that best combination. That's what optimization means. Sorry, optimization simply means looking for the best combination that will give the best output or the best results for the output. So we are going to try out various combinations. We are going to document each of them. Each of the experiments. We are going to document it. So this over here is you probably running the process or cooking the spaghetti or whatever. Then, however, you're going to arrive at a spaghetti. This looks yummy, by the way, with the combinations we saw earlier. But when you begin to alter those condiments or ingredients, our spaghetti might taste differently or even look differently according to what we use for the preparation. So that's what RSM does. So in the manufacturing settings, probably we might be optimizing a process. Let's say you work in a company that produce drinks. So you can optimize for the best combination of ingredients that will give you the best drink that is going to give customer satisfaction. You can also optimize for the processes, that's the processes it went through. You can use the same materials and use different processes. Let's say you might apply heat at a temperature of 60, you might apply pressure at a temperature of 80 to give maybe a drink, probably a Pepsi. This Pepsi over here might give you maybe different or slightly different taste of Pepsi. So RSM is simply just optimizing and looking for that best combination that will give the best results or output. That's the whole point of RSM. So let's go back to over here. So RSM is valuable for finding the best combination of factors that lead to the desired result while minimizing experimentation and resource use. You see what I was trying to say? The best combination of factors that leads to the desired results while minimizing experimentation and resource use. So you don't have to push your products to the market and get feedback. You can simply just run an experimentation on the different combinations, and RSM is going to try to give you the best combination, so you don't have to get negative reviews from your customers before altering your combinations or parameters. So it is widely used in various fields, including manufacturing, product design, quality control, to fine-tune processes and maximize efficiency and quality. So that's the whole point of RSM. And for this tutorial, we are going to be using this study over here. This is my final year project. Let me quickly scroll to the top to give you the topic of the project. Okay, this project topic is the optimization of production settings and their effects on finished crop quality. So what this project is trying to achieve, or what we are trying to achieve with this project, is to look at the various mold settings, injection mold settings, and how they affect the quality of finished crop products. So in case you don't know what injection mold is, let me quickly come over here. So this is injection mold. As you can see, this is the cup. So this is part of the machine. We are going to use the machine use various settings that will now give plastic cup. Now we are trying to find out if these settings really affect the plastic cup quality, and how we can optimize and get the best settings for production of plastic cup. So that's what this whole project entails. So to carry out this project, we went to a company, a plastic cup production company, and we had to request for an experimentation. We asked the manager to please provide us with a data set having various settings, mold settings, and they should test the cup output. That's the quality of the cups on each different combinations. So after they did that for us, we had this. This is the data set, and this is the mold settings. These in blue are the mold settings, and these are our response. These are our response. That's the plastic cup quality tested after each combination. As you can see here, these are observations. We test these combinations. Then once it brings out the cup, then we test out the response on this cup. So in total, we have over 24 experiments. So this is what we want to analyze using response surface methodology. So before we head over to our software, let me quickly explain what each of these parameters does. So this is mold temperature. This is simply the operating temperature of the mold. That's this mold over here. While it's operating, is the temperature it maintains, and that's the mold temperature. And this right here is the cavity. So over here we have injection speed. Injection speed is simply the velocity or the speed at which the molten material enters the mold cavity. That's simply just it. While injection pressure is the force at which the molten material or the molten polymer enters the mold cavity. It's as simple as that. While the cooling time is the time it takes for that molten polymer to stay in the mold till it cools to a solid point where it's then ejected out of the mold cavity. So we are studying all this to now get these responses. This weight, this is, by the way, this is weight. This is weight. All of you know what weight entails, the weight of the cup entails. So plastic cups essentially doesn't have to be weighty. It just has to be light, because most times it's used by little kids or children and adults, old age persons. So we need the weight to be as minimal as possible. Then over here we have the thermal performance. This is simply the ability of the cup to retain temperature of the liquid inside of it. That's to say, if you put a hot liquid into the plastic cup, how it retains that hotness over a period of time is going to be the thermal performance of that cup. It's not just something that is hot, something that is chilled or very cold also as well. So that's this thermal performance we have over here. While the tensile strength is the ability of the cup to restrain breakage due to tensile stress applied on it. So this is the tensile strength. To a very large extent, this tensile strength attributes or connects very much to the durability of the cup, because most times the cup is going to fall off the floor, it's going to slip from your hands and stuff like that. So this tensile strength is going to contribute majorly to how that cup lasts, the lifespan of the cup. So this is our data set, as you can see. So we call these mode settings the factors, while we call the cup quality the response, because I'm going to be using those terminologies a lot from here. Now we have 24 observations, like I said before. Now there's something I want you to let you know. Aside from just looking for the influence of each of these parameters on these responses, RSM is also has an advantage of interacting these factors with themselves and find out if they influence any of the response over here. That's to say, okay, maybe let's take mold temperature for instance. If you research on mold temperature, you find out that mold temperature doesn't directly affect any of this response over here in any way. But when it now begins to interact with other factors over here, let's say maybe injection speed and injection speed and mold temperature might now interact among themselves to influence the weight of the cup. It might interact with the injection pressure to influence the thermal performance of the cup. It might also like interact with itself. Last, if you double the mold temperature, you might find out that it also have an impact on any of the response. So this is also going to be looked at with RSM, and that's what makes RSM a very powerful statistical tool for optimization. So you don't have to just look at mold temperature and just say, oh, it doesn't affect the weight. Oh, injection speed doesn't affect the tensile strength. You might find out that at the end of the day, these two combine together to affect one of the responses, and that's one of the added advantage of response-based methodology. Now, I also want to add that, okay, let's assume now we find out that the mold temperature has an effect on the weight. How do you know if this impact is an inverse impact or a positive impact? That is to say that, let's say we find out that this mold temperature affects the weight. If I increase this mold temperature, will the weight increase or decrease? If I increase the temperature and it increases the weight, that's a positive impact or influence. But if I increase this mold temperature and the weight decreases with each increase in mold temperature, that's an inverse. It's an inverse relationship. It's an inverse. So you don't also have to look at if this influences this. You also have to look at if the influence is an inverse influence or a positive influence. So you know how to adjust your factors or your input parameters, so you can improvise that particular response. So let's say we find out that it's a positive relationship or impact. We simply just have to increase our temperature, and we'll find out that over time our weight is going to increase as well. But if it's inverse, you find out that if you now want to increase this weight, you have to decrease this, or if you want to decrease this, you have to increase this. That's what I mean by inverse relationship. And all this RSM is going to help you with all of this. And for this analysis, we are going to be using Minitab for the analysis. You can also use other software such as Design Expert, but I prefer to use Minitab because it has a user-friendly interface, and most of the tasks is already automated or done for us, so it's easy to run your analysis using Minitab. So let's head over to the software and we run our analysis. Also, one thing I would like to add is that whenever you intend to use response surface methodology, you should try as much as possible to have a very large data set, at least up to 20 runs and above, because it's going to help your analysis. Because if you just use maybe 3 observations here, it's not like RSM won't really like get the relationship or the analysis very well. But when you give it a very sophisticated data set of maybe up to 20, 25, 30 and above runs, you find out that it's going to be able to understand your data set fully. So try as much as possible to provide as much observations for your analysis. So let's quickly head over to the Minitab. I have Minitab to open over here, as you can see. So let me quickly copy my data set. Hit Ctrl C. And then you paste your data set over here. So to run your analysis, come head over to Start, DOE, because this is design of experiments. Head over to response surface, hit on Analyze response surface design. Now it's going to tell us that our current worksheet does not contain any design created by Minitab. This is because we simply just pasted our data set over here. We have not applied any analysis to it. So that's what Minitab is trying to let us know here. So we hit on yes because we want it to analyze the design. We hit yes. So over here we're going to choose our factors. Choose our factors. So quickly hit this injection speed, injection pressure, cooling time. You simply just double tap on it, or you click this and click the select here. But I've already selected it, so I'll let that pass. So another thing we should do is hit on this lows and high here. What this low and high is trying to tell us is that the minimum and the maximum values for each column. That's over here on our mode temperature. Our minimum here is 50 and our maximum here is 90. You can find out that Minitab has already done this for us. It ran through the columns and got the minimum and the maximum, so we don't need to input it manually as other softwares. So this is great. This is why I love Minitab. So let's just click on OK and hit OK. Then it's going to ask you for your responses. I'm going to choose the column we are going to use for the response. You hit on weight, thermal performance, tensile strength. And let me quickly go over this some of these settings over here. You don't really need any of this. You don't need this. Just leave this as full quadratic so you can understand your analysis better. Just hit OK. Options. Don't need to do anything here. Don't need to do anything here as well. Just head over to this graph and select this 4 in 1 over here. Hit on OK. For the result, we can have simple tables or expanded tables. Okay, we are going to use the simple tables because it's just for this tutorial. We are going to run with the simple tables. Hit on OK and click OK, and it's going to run the analysis for us. Now, for each of our response, it's going to generate an analysis for each of the response. Over here, we have tensile strength, and tensile strength is going to be compared with all of our factors. As you can see here, mole temperature, injection speed, injection pressure, and cooling time versus the tensile strength, as you can see over here. So we are going to know the factors that influences this tensile strength. So to know the factors that influence the tensile strength, you need to come over this column here. It's called p-value column here. So the more the significance, or the more the impact of that factor, the lesser the value of, the lesser the p-value. The lesser the p-value. In fact, a good p-value, it has to be 0.5 below. 0.5 below. So to know the significant value is the ones closer to 0.05 and lesser and less. So over here we find out that injection pressure amongst the p-values is the most significant, or has the most impact, because it has a p-value lesser than 0.05. Over here is 0.029, which is lesser than 0.05. So you can say that this injection pressure influences the tensile strength more than any other factor we have. And like I told you, the factors interact with themselves and with other factors. As you can see over here, you can see that mole temperature times mole temperature, injection speed times injection speed. This is the factors interacting with themselves. They also call them the square terms. So we just call them the square terms. While where they interact with other factors, we call them the 2FI interaction. That is the two-factor interaction. They interact amongst themselves over here. So just come over to this, head over to this p-value and check the value of their p-values over here to know the one that is most significant to that response, which in our case is the injection pressure. Now, if you still go through over this p-value, you find out that the square term for injection pressure, that's injection pressure times injection pressure, also have a very, it's not below 0.05, but at least it comes close, and it's closer to this injection pressure. It comes next to this injection pressure. So these two are the factors that influence this tensile strength. There are no interactions here that are significant. Maybe this one is slightly close, or so cooling time times cooling time. But for the interactions, there are no interactions that influences the tensile strength. So after knowing the ones that influences that response, to know if it's a negative or positive influence, you have to head over to this coefficient column here. So for injection pressure, we have 2.78. Now, if that value is positive, it means there is a positive impact or influence on this tensile strength. That's to say, if we increase this injection pressure, the tensile strength is going to increase with it. But if the value here was negative, what it means is that it's a negative relationship or impact. And most times you find out that if the smaller the p-value, the higher this value over here. So you just have to know if it's negative or positive to know if it's a positive relationship or a negative relationship, and that's for that. So let's say you are doing this analysis for a friend or a client, and you don't know how to explain this to the client. There is a table here you can use that will help you, and it's called the Pareto chart of standardized effects. And as you can see, the response is tensile strength, and like I told you before, the cutoff is 0.05. So the most significant values are usually very closer to that 0.05 and below it. So we find out there that we have C is the most significant, and C stands for injection pressure, like the other table told us before. And CC means injection pressure times injection pressure. That's if you double the injection pressure. It also has an impact on the tensile strength, which comes next. And the one that follows is DD, which is cooling time times cooling time, like you saw before on the other table. So that's that for that. You can just simply use this Pareto chart to quickly view the factors that influence that particular response without needing to interpret those tables above. So that's all for this Pareto chart. Now, this is our model over here, our mathematical model over here. So this is going to be used by response office to predict and to optimize for tensile strength. So you don't need to worry about this. This is going to be used by our software. But if maybe you are using this thing for educational purposes, it's good to include this to your analysis. It shows your model. Now, to know the accuracy of your model, you use this model summary table over here, and it shows the R square. The R square over here is 95.97%, which is quite high. It is very, very high. It means our model is very, very good. It's very, very good. It means that the model can explain for 95.97 variability in our data set. It can explain for that, which means our model is very, very okay. Then we have this adjusted R square. Adjusted R square. This is the R square, but it's going to penalize for the number of factors we have in our data set. So over here we have 4 factors, and it's penalizing us for that. Hence the decrease in the R square. So usually this adjusted R square is more accurate than this R square over here. Then the R square pred is the predictive ability of our model. 44.75 is not too good, but it's not too bad as well. So it's just trying to tell us the how good our model is at predicting new values. So that's that for this model summary over here. And we don't need this analysis of variance table much, because what we already need, we already have from this coded coefficient table, because there's still the p-value over here, which is same as this coefficient table over here. So we don't need this ANOVA table much. So last but the least over here is the residual plot, and this is just to show you the trend in our data set. Over here you find out that it's purely random. There's no particular pattern. It's very, very, very randomized. After all, we took the data set, we took a random experiment. That's why we have a random thread over here. So that's that for that. So we still have for the thermal performance and for the weights, but I will not be going into them much. But let's quickly come over down here to know what influences the weights the more. Okay, for the weight, the cooling time, the square term of cooling time influences the weight the more. So if you double your cooling time, it's more likely that your weight is going to be increased. Let me check if it's a positive or a negative. Okay, it's a negative. So if you increase your cooling time over time, it's going to decrease your weight. It's a negative impact, as you can see over here. But I won't be going much into that, so you already understand what's going on over here. So we head on straight to the optimization and the prediction. So to optimize, we quickly go back to our start, DOE, response office, and come over to this optimize over here. You don't have to analyze again because I've already analyzed. So you have to click on this response optimizer over here. Click on it. So what do we want to achieve? Optimization is getting a target. It's all about getting a target, a maximum or a minimum. So over here, we want to maximize tensile strength because we want the curve to last as long as possible, like for it to avoid cracks as much as possible. So we want to maximize this tensile strength. Also, we want to um, maximize this thermal performance. We don't want a case whereby you just pour something hot into the cup and in few seconds or minutes it's already cold. So what we also want to maximize thermal performance. So heat maximize over here. Then for the weights, we want to be doing the inverse. We want to minimize the weight as much as possible. You don't have to go to the gym to be able to use a plastic cup. So we want to minimize the weight as much as possible. So click on minimize over here. Then you don't need to do much, just click on OK. Now it's going to give you the combination that will give you that which you want. You can find out over here that it says our motor temperature is, you are going to use a motor temperature of 57, injection speed of 50, injection pressure of 95, and a cooling time of 15 to achieve a tensile strength, because it's not going to only give you the optimal combination, it's also going to give you the expected quality output or response. That's why RSM is great. So over here we have what to expect. We have a very high tensile strength, a high thermal performance, and a minimal weight over here. So this is our optimal combination. This is our low, and this is our high. If you remember when we started this analysis, we had to, at a point, we had to impute the low and high, but Minitab did that for us already. So this middle over here, highlighted in red, is our optimal combination. It's our optimal combination. So that's that. So if you want to know the expected, you have to scroll over here and see the expected response of the optimization. So last but not the least, we want to predict. So to predict, head over to Start, DOE, Response Office, then come over to Predict over here, click on this. Then you enter the settings you want to predict. Let's say I want to use a motor temperature of, let's say, 75, an injection speed of 75, injection pressure of 105, and the cooling time of let's say 20. Want to predict the outcome of this combination. So we want a response. You can choose the response over here. You have to choose the response. So we want to see this combination over here. What is going to lead on the response? What is going to the value of tensile strength is going to give us. So click on OK. So it's going to show you your model that I used to calculate that prediction. Like I said before, the model is going to use for prediction. So with these settings, we have a tensile strength of 33.6. That's the fitted value over here. So you can still run the same settings and get your values for thermal performance and the weight. So you can still do the same thing. In fact, let's just go one more for the thermal performance. Remember 75, 75, 105, and 20. So Start, DOE, Response Office, Predict. So we have this, but we have to choose thermal performance this time around. We have 75. We have 75. We have we use 105, and I think we use 20 over here. And remember thermal performance, I will click on OK. So these are model for thermal performance. These are settings, and it's going to give us 0.31 thermal performance, which is slightly lower than the optimized value for thermal performance. So these are output. So you can still run this for your weight and get the prediction, the weight prediction, using these same settings. Okay, another advantage of RSM is that for those of you who don't like reading numbers or figures, RSM is perfect for you because RSM can give you virtual representation of your analysis, and you can simply just look at them and find out what you are looking for, and off you go. You don't need to um, have to read all these complex or complicated values and numbers. So I'll be showing you those graphs and representation right now. So let's get into it. Come over to start DOE response surface. There's something we call surface plots. So hit it. Let's use tensile strength for example here. Let's generator plots for now, then on separate graphs so we can see each graph very clearly. So just hit on OK, and it's going to generate all surface plots for all interaction among the factors. So over here I think we have 6 interactions here. Let me quickly go back to the tensile strength to know the factors that influences tensile strength the more. Okay, the mode, the injection pressure, and the mode temperature influences the tensile strength the more. So on our surface plots, you are going to look for the injection pressure and the mode temperature, and this right here is what we care about, because these two individual factors affect the tensile strength more than any other factor. So this is the interaction. So RSM deals with 3D surface, 3D plots. Unlike your regular 2D plots where you just have X and Y axis, RSM uses 3D plots, whereby each of the factors is going to hold values for X and Y, and the response is going to be our Z axis. That's why we have these plots over here. But we can't really tell much. We can't really tell much from these plots over here. We need another one called the contour plots. That's the one that we need. And let me quickly bring out the contour plots that we need for this. I'll come over to start DOE response surface, and don't click on surface plot. We need the contour plot this time around. Click on OK, choose tensile strength, the response that you want. In my case, I want tensile strength. I choose the mode temperature and the injection pressure, because these are the two factors that influence this tensile strength the more. I want to see the contour plot. Then hit on OK. Then we'll have something like this, and you can see that in the injection pressure is on one side and the mode temperature is on another side. Then over here on our z-axis, we will now have the response, which in our case is the tensile strength. So what this plot is trying to tell us is, at a glance, you already know what to achieve with this plot. So if you want to achieve a tensile strength lesser than 24, you have to focus on this part over here. So you have to fix your mode. You have to place your mode settings at an injection pressure of 50 to maybe 67, between 50 to 67, and your mode temperature to about 50 to maybe 72 over here. And most likely you have a tensile strength lesser than 24, as you can see over here. But if you intend to achieve a tensile strength greater than 32, which most likely you want, and you have to go to that color range. I think that's it over here, and you have to trace from there. I think you will be needing a mode temperature of 90 and above, and an injection pressure of 90 and above to achieve a tensile strength of 32. 32 years. So that's essentially what's happening over here. Let me quickly do one more example so you get the grasp of it. So let's say we want to achieve a tensile strength between 26 and 28. I think this is the color over here. That's this one over here. You need a mold temperature of between 82 to 88, between 82 to 88 or 81 to 88. I need an injection pressure of 80 to maybe 89. So once you place your mode parameters at that, you are going to likely achieve a tensile strength within that range. And also note this is your hold values for the other parameters. You need to hold your cooling time at 22.5 and you need to hold your injection speed at 80. So with this contour plot, you can easily identify what your targets, what you want to achieve, and just place your parameters or combinations to fix that settings or directive is telling you. So that's all for contour plots. You can also generate all contour plots. You don't really need to just focus on a particular contour plot. Just come to response surface, contour plots. This time around, don't choose, just hit on this generate plots for all pairs of continuous variables and click on OK. And it's going to generate all plots for you, as you can see over here. So that will be all for that. Okay guys, to round up what we have learned today, to wrap up, let me quickly go back to my project so I can point out some few things and features about RSM that I feel is important for you to also learn as well. So why use response surface methodology against other statistical tools? One reason, and I feel is the best reason, is because RSM considers multiple input variables simultaneously. So because most of the times your process is not just deal with one parameters, most times it's multiple parameters, there are many. Whether you are working with a process or materials, usually there are multiple input parameters, and this is where RSM really comes in. Like this is where it shines a lot. So this multivariate approach is one of the best reasons or good reasons to use RSM for your analysis. There are also other reasons such as efficient optimization. Is purely designed for optimization, like it's best when it comes to optimization, and it aims to find the optimal combination of input variables that results in a desired response. So this is another area where RSM shines. Also, as we have seen previously, visual representation, it gives you plots and contour plots to visually represent the relationship between your inputs and your outputs. It's used for predictions as well, efficient experimentation. This is also very important. It can handle non-linearity because most times your data is non-linear, so RSM can deal with that as well in order to give you accurate results. Robust analysis. RSM can assess the robustness of a process or product design by examining the effects of input variations on the response variable. So this is valuable for ensuring that the system performs consistently in the face of uncertainties. We'll talk about optimization and balancing multiple objectives. Sorry. This is one thing I forgot to add. In some cases, there may be multiple objectives to consider, such as maximizing quality while minimizing costs. RSM can help find the best compromise among competing goals. So, in other words, you can also use RSM if your focus is to minimize cost while looking for the best quality. RSM is definitely the tool for you to use. And lastly, but not the least, practical applications. I don't know why this keeps going. Yeah. Okay, practical applications. RSM has been successfully applied in various fields, including engineering design, chemical process optimization, pharmaceuticals, and product development. So these are the reasons why you should consider using RSM for your analysis. But also there are other methods you can use to alternatives to RSM rather. You have factorial experiments, we have intervention methods, we have Monte Carlo simulation, we have gradient descent, we have genetic algorithms, we have simulated annealing, and we have cringing. You can take your time to research on these methods or techniques. I won't be doing that, I won't be covering that in this video because it's beyond the scope of this tutorial. So you can do a little research on these methods. They all have their pros and their cons. So you have to pick the one that best match your use case, like what you intend to use it for. And that will be end of this video. If you like the video, help me smash the like button, share the video, share to your friends, share to your family. If you have clients or you know someone that runs a manufacturing business or produces something, I feel this RSM is a very important subject or topic for that person to be able